Also, I want to thank the organizer for the opportunity to speak today. And Hani just talked about how the forcing from below, particularly the gravity waves and their impacts on the ionosphere-thermosphere. I will talk about the forcing from above, specifically the magnetosphere energy input and how they impact the ionosphere-thermosphere, which is particularly important during geomagnetic active conditions. So here's the outline of my talk. I will first just introduce what kind of magnetosphere energy we're talking about, and then highlight some examples of the impacts on the ionosphere and the thermosphere system. And lastly, I will just briefly mention what kind of measurements from a Daedalus mission would help further enhance our understanding of these important topics. So in terms of energy input from the magnetosphere, they mainly come from three types. Well, actually two types into the ionosphere, thermosphere. One is the geoheating, and another the energetic particles. But the energetic particles, we usually separate into two components. For the aurora particles, we mainly considering those particles are have a energy less than 30 kilovolts, kilovolts keV. And then for energetic particles that come from the ring current radiation belt, those are particles have energy greater than 30 keV. So here's an example, and shows that during this well-known Halloween 2003 Halloween storms, and which is a superstorm with DST down to about 400 minus 460 nanotesla. So in the second panel is showing the hemisphere integrated geoheating. And the third panel is the aurora power, and the bottom panel shows the energetic, more energetic particles measured by NOAA MIPAD instruments for electrons and protons. So in general, you can see that it just enormous input is coming from the geoheating with a peak close to the 9 terawatts, which is enormous. Then the aurora power is peak up to about 500 gigawatts. And the more energetic particles, ring current from ring current radiation belt, they have total, in terms of total power, they are much smaller than the other form. So here I'm just running down mean numbers for this particular event. For the average geoheating over this 3-day period, it is about 1 terawatts. And the aurora power is 186 kilowatts. And for the electrons, radiation belt, electrons is 5 gigawatts, and the protons is 12 gigawatts. However, even though the energy from the more energetic particle from a radiation belt is small in terms of total power input into the upper hemisphere, because they have a larger energy, higher energy, and they penetrate much deeper into the atmosphere, therefore have a different kind of impact into the system. So what I'm showing here is the vertical attitude profile, attitude distribution of ionization rate by the different energetic particles. On the left is the aurora electrons with energy less than 30 keV. The middle is the MIPAD electrons with energy greater than 30 keV, and the protons on the right-hand column. So you can see that for the aurora part electrons, it's about 106 kilometers peak height, and for MIPAD electrons, which penetrated much deeper, all the way down to the mesosphere at about 73 kilometers. And for this particular time, the MIPAD protons at similar heights as the aurora electrons. So they do have so the peak height actually pretty much depend on how the mean energy of those particles are, and on the bottom, I'm showing the 2D maps of the ionization rate distribution at their peak height, and at the 106 kilometers for the proton for the aurora precipitation, and you can see this oval shape, which are usually the intensity of the ionization is pretty much depend on the total number of those particles coming into it. Then the electrons, you can, for the MEPAD electrons, you can see even more intense ionization at a lower altitude, 73 kilometers, and for high energy protons, the ionization rate is much smaller. See, the color scale is different for the different particles. But their peak height is similar to what the aurora electrons are for this particular time. And of course, things changes with time and the time. And also another impact, because energetic particles impact, they have profound influence on the ionosphere properties, such as conductance, heat, and the heating. And showing here are again, two examples. One example is at the same time, and the top row shows the conductivity and heating due to aurora particle precipitation, and the bottom I also added the MEPAD and more energetic particles. And so you can see that the energetic particle at the second peak at the lower altitude, and even have more intensity than the aurora precipitation. So as I said, that the majority of the energy coming to the thermosphere ionosphere system is through Joule heating. Therefore, it is not surprising that the thermosphere is so disturbed during major storms. So here again is the same event. I'm showing here is a model simulation results here. So the black line is the reverse, the DST index, and the red line, the dashed red line, is the Joule heating obtained from the AMAT data simulation, and which has a 5 cadence. If I smooth that into 3 hours period, so you can see smooth the red line here. And surprisingly, this the smooth Joule heating and the DST have a very good correlation. It's a 0.9, but the DST lag behind the Joule heating about 2 hours. So the middle panel shows the temperature, globally average temperature at the different height, at 5 different heights, and these are the percentage temperature changes. And so if you see that the temporal variation can be closely related to the peak of whenever you have a peak in energy input, the Joule heating, and you see the peak up. And so there's very good correlation between them. And also there's a time delay about 2 to 3 hours in the global thermosphere response. The bottom panel shows the neutral mass density percentage change at the same 5 different heights, and they show the similar global response. And here's another event, well-known event, the March 2005, the St. Patrick's Day 2015 events. And again, similar plots. On the top is the black line is the reverse the DST, and the red solid line is a smooth Joule heating. The correlation between these two have the correlation coefficient 0.5, and this time for this event have a best correlation is with a time lag of 3 hours. We also see the similar profile if you compare with in both density and the temperature and the density variation at the different heights. So pretty much, if you look at this correlation between neutral response to the Joule heating and the dissipation, you can get a very good sense about how thermosphere, ionosphere on the global scale, how they will respond to the energy input. So it's some way you can really predict what the response would be. However, if you look at the locally detail, how exactly ionosphere, thermosphere response to the Joule heating dissipation, it is very, very complex. So this is at the 2 incidents. On the left side is at the 6:30 UT on the March 17, 2015 event. And the top row shows the Joule heating, and the bottom row shows the neutral mass density at 470 kilometers, the height of the swarm altitude. And this I also plotted the swarm mass density, neutral measurements shown by the circle dots here. So for this, at this particular time, you see there's a heating over the polar cap, and you have very large density enhancer over there. So the swarm just passed through the tip of this enhanced polar cap density bulge. At the 1430 UT, however, this is during main phase of the storm, and the geoheating is much more enhanced, and they also have a larger response in the neutral mass density. However, if you're comparing the mass density variation and the neutral, the geoheating dissipation, they do not really look like exactly the same thing at all. So the density mostly on the night day side, as well as you see this kind of ton of kind of enhanced density structure across the polar cap. And here, however, the geoheating, you can see the most geoheating on the dawn and the dusk side, and it's not really very good direct correlation between geoheating and density variation. So look, on the local scale, the relationship with the energy dissipation in the thermosphere, it's really complicated. And of course, and for this one, you can see the swarm satellite measurements, see the enhancement actually all the way across. So, but the model shows kind of buyout here. So there's a mismatch between simulation results and the measurements for this particular case. So just to remind you the geophysical conditions for the March 17 event. So here is the solar wind, the IMF, BY, and the BZ component on the top panel, the cross-power potential drop, particle aurora power, and the geoheating power here. So so you have, first you have a geoheating started enhancement about the 6 UT, and with a smaller, then the major storm actually come in after 12 UT. So, and there's one short period, here's a southward excursion in the IMF, and you can see the big jump in the cross-power potential drop. Actually, this southward IMF excursion produced property penetration electric field, which is really shown up in the ionosphere response as well, which I just highlight a little bit later. So another way to give you a sense of how complex the thermosphere response to the energy input from a high latitude. So I made up this movie. On the left side is height integrated geoheating. Then on the right side is the neutral mass density at 470 kilometers, and also highlight the swarm A trajectory by the magenta colored dots. So you can, as the movie goes on, you can see how the one satellite mission could measure and could miss lots of things as well in terms of because of the complex response. And the vector here are the neutral wind at 470 kilometers. Okay, so this is at 5 UT just before the first enhancement of the geoheating. So you can see here's the first one, geoheating enhanced, and you see the weak response in relatively speaking. Then the second one starts to come in. So you can see dramatic increasing. Now you can really see how dynamic the thermosphere response are in both density and the neutral wind. And so the neutral wind actually reach almost 1 kilometer per second, so which is enormous. So you can see by the time end of this event, and the entire thermosphere is just totally elevated. Okay. So next I'm talking about the impact of ionosphere, and I'm using well-known parameter for TIDs, which is electron total TEC measurements. So I'm showing here are the delta TEC, difference TEC at the 3 different locations, the European location 10 degrees east, the North American location 85 west, and the Central American location 65 west. So for the different locations, you can see there's a lot of similarity. You can see the TIDs as indicated by those slant TEC structures at the different locations, all shows up at the 3 locations. However, differences are very obvious among the three locations. One interesting features I want to point out is here. So this is the European sector after about 14 UT. And you can see that at the lower latitude, you see more coherent, larger scale TID, whereas on the top forward of that, you see the fragmental and the fluctuating, relatively smaller scale TC mesh enhancement. If you look at, so this is time actually after 14 UT, the European sector is started rotating into the nice side aurora oval. So if you compare with the aurora energy flux and plot in the same fashion, you see that this dashed line I overplot here, it's just at the equator edge of the aurora. So what is showing here is those relatively smaller scale density perturbations or TC, different TCs are really due to the enhancement of aurora precipitation. So it's caused another layer of complications in terms of how the ionosphere responds. There's whereas at the lower latitude, and you can see the TID develop at the equator of aurora zone. So for the American sector, most striking feature is the relatively very slow kind of TID's features, which is about 160 meters per second, which is unlike the typical TIDs, which has phase speed about usually between 500 or to 800 meters per second. So it's very moving. It turns out this thing is actually, it's not traditional sense of TID, rather it's due to the SAP induce the aurora activities. Then in the equator region, TIDs you can see coming from both northward and the southern hemisphere. From northern hemisphere, they cross each other about minus 10 degrees south, which is the magnetic equator in this longitude location. So you can see waves from both hemispheres cross each other at the magnetic equator, and then some of them cross over and some of them bouncing back. So it is a really complicated structure in terms of ionosphere response.
And Lou, there are 2 minutes left.
Okay, all right, yeah, almost done there. So just to show that we are not really producing realistic features using our model when you're driven with realistic highlighted input, and here comparing with the GNS TEC measurements shown on the right, and indeed we produce most of these features in the as observed and as highlights. So I just basically highlighted the main features by the standard dash line. However, and in addition, we see the sunrise effect and in both model and in the observations, and the PPE effect, which produce this pair of positive and negative TC perturbations. However, there's also some quantitative disagreements such as circled here. For example, here's vertical structure in the observation, but we see as weak TID, and here's the TIDs in the measurement, but we see not similar TIDs. And again, the phase speed for this event is simulation shows much fast. Okay, so another movie just to show you on also the complexity of TID response to the magnetic storm, and particularly the energy from the magnetosphere. And this is a delta TID, and so this is during main storm. You can see the TID is coming from both hemispheres. They cross each other. Some are refracting, some are going back. But the point is, global scales, there's no very clear coherency at the different longitude and the different, local time, different longitude or local time or latitude. So it's very, very complex. Again, so if you're just have one satellite, you're really missing lots of dynamics in the missing lots of dynamics shown in the system. Okay, so just finally, just a few words, what kind of measurement from a Daedalus will be particularly helpful to better understand the energy input and ionosphere thermosphere responses to the storm. And for, of course, we need, for energies, we need a good measurement of electromagnetic field or on drift. And then for temperature, for pitch angle resolved energetic particles, for electrons, ions, for electrons from 10 eV maybe to MeV, and for protons or ions, maybe 10 eV to 100 MeV. So try to cover the major energy range of those sources particles are, and the parameters. Basically, we want to fully understand the response. We really all the neutral parameters, ion parameter, density, temperature, composition, which are very important. Then for uneutral coupling, one particularly important thing is you need to have a very good vertical sampling, because both neutrals and ions, their property changes dramatically with altitude, and therefore their electrodynamic coupling would change. So, and also better increase in the sampling rates will also help better understand the temporal evolution of the system. Okay, so I'll just stop here.
Thank you very much, Gang. It was a very interesting presentation.